Today we're here at RWDI's facility doing the wind tunnel testing for the new Gordie Howe Bridge. What we're doing today is what's called the aeroelastic modeling, meaning that we're testing a full bridge model. And this is really part of the design process for the bridge. It allows us to get the design loading and ensure the stability of the structure. Today what we're testing really covers three areas on the bridge design. One is the overall stability of the bridge against high wind conditions. The second is to make sure that under normal everyday wind conditions that we don't have vibrations. They're going to make the bridge uncomfortable for the pedestrians. And the third is under relatively high winds from a buffeting standpoint to make sure that we have enough strength designed into the bridge to carry the wind loads. So especially for the Gordie Howe International Bridge, where we have a very long 853-meter main span, it becomes absolutely necessary to do wind tunnel testing to assure the safety and the stability of the bridge.
We build two different versions of the model. The first round of testing we do is with the sectional model, where we model a short section, usually about 15 to 20 cable lengths of the center of the bridge, just so we can go through all of the different stability tests for a bridge, where we test it with every possible configuration that could go on with the bridge. We test the bridges with icing conditions, different variations of railings, different barriers, and different angles of attack just to check the stability of the bridge. We also do, which is in our wind tunnel right now, the full aeroelastic model of the entire bridge. And what this is to do a double check and make sure that the stability of the bridge is going to be what it's supposed to be over the entire length of the bridge, and there's no surprises. To create our models, we use virtually any type of material that we can use to get the results we need. But first we design the model in 3D first. We use SolidWorks, where we can apply all the properties of each of the material, example for plywood, aluminum, and stereolithography resin, which we use to create most of our parts from. And in that, we assemble it all together so that the bridges will react as it would at full scale in real life. In the wind tunnel, we have some large turbines that spin at high rates of speed to force air through an enclosed chamber. And we can manipulate the wind that these turbines are doing to match the local wind data for wherever we're testing a project. And we take the information from the local wind collection sites, such as, for this case, the Detroit airport, and we scale that and factor it to match in our wind tunnel.
For major long span bridges, wind tunnel testing is one of the few items that we still have to do by an experimental method. Computer programs are just not far enough advanced where we can do a computational analysis of wind on a structure.
The bridge has to be assessed both for its completed configuration and also for the construction to ensure that we have a stable bridge while they're constructing and also in the completed project. The bridge model that we have is a full-size scale model of the bridge at 1 in 230 scale. In a long span bridge, the wind engineering is an essential component of the design process. We are at about 30% design, but at that stage all of the major design decisions are taken. And so what we're doing now through these studies is confirming the loads that have to be used in the final design, and also the load combinations with wind, with live loads, and with the dead loads of the bridge. So the completion of this phase will allow us then to complete the design and get the construction underway in the near future. The results of the wind tunnel analysis that has been undertaken has shown that we have a very stable bridge. The cross-section is very aerodynamically stable, which will provide a very comfortable ride for the users of the bridge.